But you can't vary the duration that it stays open. Because even though you've got a fixed size orifice, it's basically a valve. It pops open, it pops closed. But you can vary the amount of time that it stays open. And I think in the long run, that and the butterfly valve and a computer program, I'm sorry, but I think it's going to take a computer program to do this properly.
Yeah, I agree.
Doing it manually.
But I think once all those pieces fit together, I think we will actually have throttle response out of hydroxy.
Because he's already demonstrated here that it works.
Apparently, that's what I'm trying to
You
figure out.
can
How
get, you can get the engine to work, it's just, as you've discovered, maintaining that air-fuel ratio.
Yeah, I found that seems to be pretty key. The backflashing thing, I had a class last fall or something, and it was on bioenergy, and we were talking about tank hydrogen. But they have to run if you're running on tank hydrogen, they have to run lean. Because if you run any rich at all, you have backflash. So I'm wondering, maybe we're running rich, at least according to what they're saying.
Well, I would love to see. Believe me, I've tried.
No, I know.
I've tried everything from about 1%. I'll tell you what, you can flood it out. You can flood the engine out by trying to feed it too much hydroxy. And that happens when you get down to about 3 parts air to 1 part hydroxy. You will flood the engine out. It will literally stall through the flame.
The issue with running lean, though, as you've already discussed it in a few slides back, is that your NOx emissions go up.
But if you run, if you adjust the timing, because the lean or the NOx production is solely based on combustion temperatures. So if you're, that piston's still up here, you're putting the hydrogen in, you're sparking, and it's still coming up here, and it's burning, and it's hot, and you're gonna have a lot of NOx. But if you get it closer, and it's moving a little bit faster, right?
Well, you'll have combustion temperature issues when you're boosting, but when you're running straight hydroxy, you won't.
Put your hand around the exhaust.
Are you kidding? It'll get cold. The engine will get cold.
Yeah.
Okay, when you run a gasoline-powered engine, run it at 3,600 RPM, wire, fixed scenario. Exhaust temperature, right at the exhaust valve is going to be 650, 700 degrees. On hydroxy, you're lucky if you can reach 150 degrees under the same conditions. So the temperatures and the formation of oxygen, nitrates,
and that's proof of another process going on.
I'm sorry, say again?
That's it, and that is the proof of another
I'm not sure
process.
there's any proof of any. All I'm saying is that
Process, well,
the
it's another-
temperatures, I'm saying that the thermal transfer from the combustion of hydrogen to the walls of the engine is next to non-existent.
Right.
I believe that, I can't prove it right now, but I think it will eventually be proved that what we're dealing with here is a concussive force. It's not combustion. It is quite literally an explosive reaction. And there's no time for any thermal transfer. Combustion, you have kind of a long process of burn. So there's a period of time there where the internals of the engine can heat up.
Well,
Hydrogen, it's like that. It's done.
What you're seeing is a different process. Like Hutchinson has a knife. You can see it on the YouTube. He has a knife that's in a metal plank, and it's cold. The process is done with.
Now, I misspoke if you meant that it gets cold to the touch.
Well, no,
It's much cooler than
Gas.
the burning of gas.
That's a fluke.
The difference between detonation and deflagration.
Yeah,
One of
it's the
them
difference between combustion and conflagration.
One of them is less than the speed of sound, and one of them is over the speed of sound.
Yeah.
But the mind-blowing thing is about this, back to the oxides of nitrogen. Yes, the engine's cool. Yes, you can put your hand on it. But inside the cylinder, where the combustion is actually occurring, the temperatures are very high. It's just none of that heat gets transferred to
Do
the
you
block.
think we might have a problem with it? I always
There's
thought
localized
I always thought there should be an
There's heat
increase
there.
in oxides of nitrogen. I've never been able to prove
There's heat there, but it's difficult to measure the temperature inside inside the combustion cylinder while it's running. I mean, you get a heat probe in,
Yeah.
because you can't measure the temperature at the cylinder head interface. You have to measure the actual, you have to have a probe inside the actual area where the combustion is occurring. And to prove that, when you're playing with your torches, right, you know that you can melt rocks with it. You can make glass out of rocks. You can cut through stainless steel. You can melt tungsten. Yet you can take the flame and pass it right over your hand and barely feel the heat.
Well, there's an effect to that too, because the central core of the flame column in the torch is vacuum. And basically what we've got is the torch flame is hollow, and the insides of it is a vacuum. Now, I can prove that too when we get something like copper. If we take the torch and we direct it to copper and we start vaporizing copper, you can actually watch the green copperic oxides being drawn right up into the central column of the torch. It's a fascinating effect. I put a YouTube video out there showing that effect. I wondered if anybody would catch it. So what the heck was that? You know, it was very interesting to watch because all of a sudden you start vaporizing that copper. All of a sudden you can see the green copper oxides coming right up the center of the flame column. Very interesting to see.
What if it's not vaporized?
I'm sorry, say again.
What if it's not vaporized?
Well, it's, I tell you the truth, it is a good point, because I can't prove that it's vaporized. Frankly, I think it's ionized.
Right.
Yeah,
I think it's quite literally ionized.
There you go.
I think it's one step
There
beyond
you go.
vaporized. I didn't want to shock anybody with what
No,
I
I
really
agree.
think it is.
I think it's
Quite
vaporized.
frankly, I think we're dealing with copper ions at that
Yeah.
point.
The other aspect.
And I believe that that's where your temperature comes from, is now all of a sudden you're burning copper with ionized copper.
Right.
That's why
That's the
a torch that should only be about 600 degrees in temperature can all of a sudden be 6,000 degrees
Exactly.
temperature when I'm drawing
It's
in
like,
tungsten
it's
into
like that
See
flame,
what I'm going?
it's like that flame somehow in the chemistry
not
of
cutting
it,
with
it
hydroxide, I'm
matches
cutting
the
with
melting
tungsten.
point of whatever
No,
material that you're
Because
trying to cut.
I've now got an ionized column, a gaseous ionized column of that material in that torch.
It matches the melting point of whatever you're trying to cut.
That's just my theory, I got no proof. That's my observations when I've
You're
seen
on the
it.
money.
I got a couple of comments. The nitric oxides, the other aspect to that is residence time. So if you have hot temperatures, but for not very long, then you
Doesn't have time to form.
Yeah. And then there's actually, I've been researching this, and the last source on the paper is this source by another, I think another university in South Korea, and the paper is titled "Some Comments on Brown's Gas and Implosion" or something like that. And they, go through how, you get the 6,000 degree, they say 6,000 degrees Celsius flame temperature with, basically Brown's gas. That's what they say. And then with regular hydrogen, you get 2,700. And, this paper tries to explain the theory, and they do have some, I don't understand it, it's a little bit over my head, but, if somebody had the interest to go look.